Hey everybody, Mr. Grove here. We're going to talk a little bit about atomic structure and some basic chemical bonding today. And so first, we'll talk about the nature of matter and atomic structure. So the atom is the smallest unit of matter that we can't really break down any smaller without losing properties of that element. So if we had like an iron atom, we can get smaller than that, but if we do, we no longer have properties of iron. So atom is as kind of small as we go. The smallest part of an atom is for elements, and so as you can see over here on our periodic table, we have 100 plus elements, and about 92 of them are naturally occurring, and then some are artificial. And so when we glue these atoms together, that glues in a way called chemical bonding. So when we combine elements to make a compound or combine atoms to make a molecule, then that forms what's called a chemical bond. So, but before we go into that, let's talk a little bit about atomic structure. So atoms are made up of protons, electrons, and neutrons. And so the protons are represented by the atomic number, and so the atomic number is always the smaller number on typical periodic table, and that's the number of protons, and that would also be the number of electrons. And so if we are dealing with a zinc 65 atom, 65 would be its mass number. So if we want to know how many protons a zinc 65 atom would have, we would find zinc. So here's zinc, and we would see it's got 30. So that's going to be 30 protons and 30 electrons, because a normal atom has to be electrically stable then. Neutron-wise, because electrons are so much smaller than protons and neutrons, we don't really count them as having mass. And so what we would do is say electrons are basically massless. And so the mass number here of 65 is going to represent the neutrons and protons. So 65 neutrons and protons take away 30 protons, and so what we would be left with would be 35 neutrons for this particular atom. Let's try one more. Titanium 57 is our atom. So find titanium. So here's titanium. And we see that it's got an atomic number of 22. So that means 22 protons, 22 electrons. And the difference then would be 57 minus 22, so 35 neutrons. And so that is some basic atomic structure. The thing is, though, if we're limited to just elements, that limits us only to about 100 substances on Earth. But we want way more than that, so we've got to glue them together. And one type of glue is what we would call ionic bonding. And so ionic bonds are formed by ions, and that's when we have gained or lost electrons. And so ultimately, all elements want to be like these guys over here. These are the noble gases, and they are kind of perfect in their electron configurations, that they are completely full on their outer shells. So if you are not a noble gas, like all of these guys, then that means you are not quite happy and would like to do something to have electron configurations like the noble gases. So that means either gaining or losing an electron. So if you are a sodium atom, so sodium, we find it's got 11 here, so 11 electrons. It's not happy that way. It wants to either be like argon or neon, which are the two closest noble gases. Well, to be like argon, you're going to have to gain 7 electrons. That's definitely a little bit tougher than to be like neon, where all you would have to lose is 1. So sodium would much rather just lose 1 electron. So if it loses 1 electron, then that means it would be a +1 charge. So our sodium ion would be +1. Because it lost an electron. So it's got to try and find somebody that might want to take that electron. So if it comes in contact with chlorine, chlorine is 17 electrons. So here's chlorine 17. So it's really close to being like argon here, which would be 18 electrons. So it's just wanting to gain one. It could lose 7, but that would be way harder. So gaining 1 electron is easier. So by gaining 1 electron, it would meet its happiness requirements of being like a noble gas. And that's why this is a perfect formation for these guys. Sodium loses an electron, chlorine gains it, and everybody is a winner. And so the happiness is shown in the strength of the bond. And something like sodium chloride, which is table salt, has a really high melting point and a really high boiling point. So that's a really strong type of glue. So that's ionic bonding, gaining and losing of electrons. Covalent bonding is going to be when we are sharing electrons. So if we have this hydrogen here, hydrogen has 1 electron. It would really like to be like helium-2, so it's trying to gain 1. Well, so is this hydrogen. It's trying to gain 1 as well. I want an electron. No, I want an electron. So they're both wanting. It's not going to work, and so they work out the sharing arrangement. So this hydrogen says, okay, I'll loan you my electron part of the time. This hydrogen says, okay, I'll loan you my electron part of the time. Part of the time, I'll feel like helium, the noble gas. Part of the time, I'll feel like helium, the noble gas. And you know, if you've had siblings, that sharing just never works quite as well. And so that glue of the covalent bond is not going to be quite as strong as our ionic bond. And that's why most covalently bonded things have lower melting points and lower boiling points. So when we join the atoms together covalently, oftentimes we call that a molecule. And the sharing can be done a couple of different ways. We can have what's called a polar molecule, or we can have a nonpolar molecule. And so the polar molecule is going to be when our sharing is unequal. And our nonpolar is going to be when our sharing is very fair and very equal. So in this case, our hydrogens are the same size. So the share is going to be very equal. You can have my electron half the time, you can have my electron half the time. So half the time we're both happy. But in the case of oxygen and hydrogen, oxygen's 16 times bigger than hydrogen, and so the share is going to not even close to be equal. Oxygen gets the electrons the majority of the time, and because of this, the molecule is going to have an electrically charged end. So having the electrons will give the oxygen a negative charge to it, and not having the electrons would give the hydrogens a positive charge. And so that creates a polar molecule. When it was an even distribution, that would be our nonpolar molecule, because there's really no charge because the electrons are evenly shared. The polar molecule is going to make the glue just a little bit stronger between molecules, and in this particular case, it's a special kind of strength called hydrogen bonding. And so hydrogen bonding is when we have hydrogen involved in this polar bond, and so our oxygen here was negative, positive, positive, and so opposites attract, and so the bond between these two molecules right here is going to be the hydrogen bond. So hydrogen bond here, hydrogen bond here. However, this is not a hydrogen bond. This would be the covalent bond. Okay, same here. These would be the covalent bonds. So that hydrogen bonding, it's a relatively strong little bond, and that's going to give water a whole bunch of really special properties that we'll talk about in Chapter 2, Section 2. But that is some of the covalent bonding. Lastly, we just have one thing. If we're dealing with two elements and we're trying to just kind of real quickly predict, is it going to make an ionic or a covalent bond? There's kind of a quick and easy way that we can do that. And so if it has a metal and a nonmetal, so a metal and a nonmetal, then we know it's going to be an ionic bond. Okay, so a metal and a nonmetal. If it has no metals, so just a nonmetal and a nonmetal, so two nonmetals, then we know it's going to be probably a covalent bond. And so this jagged line here, this is our divider. So you can see there's a whole bunch more metals on this side than there are non-metals on this side. So if we have a one on here and one here, that would be our ionic bond. So let's say we had manganese oxide. MnO was our formula. So here's Mn, here's O, one on each, and so we would call that an ionic bond. If we had sulfur trioxide, SO3, so we have a nonmetal on the right side and another nonmetal on the right side, so this would be a covalent bond, most likely. Okay, so ionic or covalent. There's other kinds of bonds like metallic bonds, but we won't really talk about them in this section in biology. So hope that was helpful, and we'll see you in class.